Hello. Welcome, everyone. Feel free to say hi if you're there. Hi to all those that are already here. Feel free to say hello in the chat. It'd be great to hear from you guys. I've got the chat open, so I'll be able to see any comments or questions come through as we get started. So welcome. Hope you're all having a good weekend and keeping warm if it's kind of cold where you are. We're looking at the binomial distribution today. So this is a kind of key part of the probability and statistics side of the A-level course. But yeah, do feel free to say hello in the chat. It'd be great to hear from you as we go through the topic. Any questions and answers as we go would be great. So I'm going to share the screen shortly, but I hope everyone's doing well. And as I said, we'll be looking at binomial distribution today. Hi, welcome. Hi. Oh, excellent. Cool. Lovely to see messages coming through. Maria, let me know if you've done this topic before. If this is something you've looked at, have you done the binomial distribution before, or is this brand new? Because it is one of those topics that I think is quite a new idea at A-level. So do let me know if this is brand new to you today. I'm going to share the screen and we'll get started shortly. But welcome. Oh, okay, excellent. So it should be a nice little bit of a revision and also kind of teasing out key points that get examined each year as well. It's been on the A-level course for quite a long time, so it is an important topic, an important part of the statistics in the applied course, but it nicely overlaps with some of the stuff we do in pure as well, the idea of like a binomial scenario. So welcome if you're just joining, do feel free to say hi. Hope everyone's keeping well. I know it's a big long term up to Christmas, so you've probably covered a lot of content in all your other subjects as well, I'm sure, but welcome. And thank you to those that have joined already. I'm going to share the screen and we'll be getting started shortly. So we're looking at the binomial distribution today. Do let me know if you've also covered this before, or if this is new to you, to give me an idea of what we've actually seen and if this is a new topic. So binomial distribution, I think it's a brilliant one to take on. It's a huge part of statistics, actually, and it ties into lots of other little subtopics like hypothesis testing. So we'll get started. But yeah, welcome to everyone that's joined. Thank you for joining so promptly. And as I said, as we go through this session, feel free to ask any questions, get me to go back, or share any answers as well if you're feeling quite confident with it. And we'll also talk about sort of using the calculator and skills that feed into this topic as well. Brilliant. Right, let's get started. So I'm Max. I'm the lead maths teacher at Snap Revise, and I did a degree in maths a few years ago, and I've been teaching A-level maths for the last sort of 6 years or so, and GCSE and Key Stage 3 as well. But it's been an interesting time to teach the course as the kind of courses have changed as well. But this topic has been on there for a long time. So there's a kind of bank of questions we can really turn to for binomial distribution. And that's what we're going to look through today. So do feel free to say hi, welcome. And if this is the first session you've been to on a Sunday for Snap Revise, welcome. Hope it's useful and you enjoy it. Here we go. We'll keep going then. And welcome to anyone else that's just joined. So what we're going to look at today specifically is understanding how binomial expansions can be used to calculate probabilities. So you might have also seen binomial expansion within the pure side of the course, which I still also think is quite new at A-level. And then we're going to look at when to apply a binomial distribution in statistics, and then look at how to calculate probabilities from that. So this is really important as a kind of bridge between pure and stats, and also year 12 and 13 stats content. We won't specifically go into hypothesis testing and some of the harder stuff, so we're really going to just set the scene with this topic. So let's get started. Some kind of key things we should hopefully know before, some of it's quite careful, rigorous notation, is this whole thing here. Who has seen this before? Please let me know if this is new to you. And we can sort of often see this on the calculator as the button that looks like this, the NCR button. Let me know if you've seen that. The way we would actually read this notation here is N choose R. And we'll kind of explore what that means today. But I found that this was something very new to me when I started A-levels, that I'd not really seen this sort of thing before. Excellent. So some of you have seen this before and you recognize this notation, but either way, it's probably still quite new. even if you've done a fair bit of work on this. Now, some examples, I think they do give you this in the formula book. Hi, welcome, Taha, welcome anyone else that's joined as well. I'm just going through some kind of key background information we should know, and we're going to really tease out ideas within the binomial distribution today. So this notation here, the exclamation mark, we might recognize there's a special name for this type of thing, and it's called a factorial. So I'm just sort of setting up things that will be handy for this. And what a factorial is, n factorial is basically 1 times 2 times 3, all the way up to whatever n is, all the numbers times together. Really important for working out number of combinations of stuff. That's effectively what we're using it for here. Now, in pure maths, if you've done binomial expansion for something like this, you might recognize it'll be a to the n, x to the n, plus, and then you do n choose 1, which is actually n. Then you take 1 away from the power, and you add 1 to the power of b, and it goes all the way along until the last term is b to the n. So if you've seen binomial expansions in pure, it's quite helpful, especially where a lot of this notation is concerned, and using the calculator, because then we obviously see the binomial within the binomial distribution of stats. Now, in terms of probabilities, just some key ideas we should know, and then I'll get on to some of the newer bits of this topic. So a sample space, does anyone know what that is? There's a few kind of key words and terminology. I'll just whiz through quickly. So a sample space, what is that? So we have set theory, and we also have some other kind of key ideas feeding in. So if we call A is a group of outcomes, what is a sample space? Now, you might have done this like way lower down the school. A sample space, so a sample space, let me know if you know. Of basically all possible outcomes. Okay, so that might be something you've seen before. And then just in terms of the kind of basic notation, P of A means the probability of event A. And then you might have seen, even at GCSE, this notation with the prime, with the dash, which means the complement. So probability of not A, not occurring. So hopefully all of this stuff is stuff you maybe are very familiar with. We're going to get onto some harder bits in a second. The other thing as well, some kind of key ideas you might have seen are independent and mutually exclusive events. So let me know if you've seen those before. But there's actually some very specific conditions we look at A level, and it's that the intersection is equal to the probability of the two things times together. So it might be that you do that in year 13, it might be that you've seen it now, and independent means they have no effect on each other happening, and mutually exclusive means that they can't happen at the same time. So mutually exclusive, so what I'm going to say for this one is that the union, there's basically no intersection, so the chance of either thing is just the probabilities added up. So in mutually exclusive, they can't happen at the same time. Right, we're going to move on. So whether you're doing your exams with AQA, OCR, or Edexcel, the binomial distribution is crucial. It's a huge part of the A-level applied side of the course, really important part of the statistics. So we're going to set up the distribution and look at some of the typical exam style questions and ideas we have. And I know that some of you have seen this before. For some people, this is revision and so on, but do let me know if this is brand new. So what we have is, if we think about this as a binomial expansion, P and 1 minus P, and then 1 minus P is basically like the probability of the event not occurring. So I'm really going to just break this distribution down here. Right, so have a little think if we can work out what this might be represented. Any ideas? So the probability P to the power of R times 1 minus P to the n minus R. This is basically, so this is like P times P times P, R amount of times 1 minus P, the remaining amount of times. So if we try and think, what is this thing actually representing? This is basically a multiplication across like a massive tree diagram. So it's like the probability of something happening. If you think back to GCSE tree diagrams, where you go across the branches, all the different routes, like win, 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 lose, lose, and you combine all those together. As you go across branches, you multiply. So this is basically like the probability of it occurring R times whatever that is, and then not occurring the rest of the amount of times, n minus R times. And so like it's a very specific set of branches on a big probability tree diagram. So if we can kind of understand that from that expansion, it makes the binomial distribution a lot clearer. So let me just write that out, but let me know if that makes sense. Welcome to those just joining. Lovely to hear from people in the chat. Please do feel free to ask if you need anything clarified, and also share answers. So this P to the R times 1 minus P to the n minus R is basically like a very specific multiplication along a massive tree diagram set of branches. So it's the probability of something happening R times and not happening the remaining times. So we're really just setting the scene for what's going on in the background of the binomial distribution. The rest of the times. So then finally, putting it all together for this bit here, can anyone sort of suggest what that actually is? So n choose R, as we said, we read it like that, n choose R times P to the R times 1 minus P to the n minus R. Now that, to most people, just looks kind of like scary maths, like what is going on there? But can anyone think how using sort of this description and then remembering what n choose R actually means, what this thing here is actually describing? What could that be talking about? So if I multiply n choose R, which was this important combination thing that gets us combinations of stuff happening, times by this, which is a probability, times by this, which is like a remaining probability, can anyone sort of think what this mechanism is doing? Because this is fundamental to the binomial distribution. And you might know loads of little shortcuts on your calculators for doing the binomial distribution really easily. But this is actually what your calculator is doing in the background. If anyone can suggest maybe what that is working out, feel free to do so in the chat. But I'll try and I'll write the definition and then I'll just talk it through if we're still unclear. Absolutely right. Yeah, super. Thank you for the comment there. It is actually the full-on probability of it happening R times, and out of n choose R times. And the reason for that, if I put it back in light of the context of a big tree diagram, so if I just write what you've said there, but superb, the probability of it occurring exactly, and this is important, when you think about GCSE tree diagrams, you might remember sometimes you have to do a few things, of it occurring exactly R times in n amount of trials. So I'll put a little thing around that, in n trials. So remember, like we said, this specific thing is like one branch of win, 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 lose, lose. But actually over, say, 10 things, if you wanted 7 wins and 3 losses, there's not just one way of doing that. There's loads of different combinations of how you could have 7 of these and 3 of these. And that's why this mechanism is important, because it's effectively adding up all the other branches that are doing the same net effect. So that n choose R is kind of fundamental to the amount of combinations of having that result. So like if I said I want 7 wins out of 10, I'm effectively saying I want to win 7 times and lose 3 times. So how many ways can that happen? Times by the probability of it actually happening. So that's really important. If you follow that, that's brilliant. That shows a really secure, sound understanding of the mechanics of the mathematics going on in the background there. So do let me know if that's unclear or if you want any of that re-explained, but really well done. And I think that's a good thing to just consolidate. Sometimes you need to think that through a few different ways. And typically we're not drawing massive tree diagrams out at A level, but if you can think of it like a tree diagram, it actually makes the formula make sense. Very good. Now this, I don't know if any of you guys have done this explicitly. It's in a lot of the textbooks. This is a really common exam question. And the question is like, when would you model something as a binomial distribution? Does anyone know any of the conditions? Like they can be paraphrased quite quickly, but it's the criteria. And I've seen this nearly every year in a mock or the real thing in an exam paper where they say, like, when is a binomial distribution appropriate? What conditions would we use a binomial distribution? Does anyone know any of the key ones that the question would be looking for? So this is almost like we can bullet point list these. We should know, why would it be a binomial distribution? What would that mean? Must have to be the case about the information we've got. So I'm going to list these off, but do let me know if you know any or if there's any I haven't said yet. So here we go. So feel free to let me know in the chat. So one of the conditions is that there are a fixed number of trials, which we are calling n. Call that n. Any other conditions we know? So again, this is so examinable. This would be like an exam question. Another condition for the binomial distribution is one that people sort of paraphrase because it is what it says on the tin. Each trial. Yeah, all good, thanks. How are you? I hope we're all well. Thanks for joining, and do feel free to share any answers and questions as we go. We're just going through the conditions of a binomial distribution because this is such a common exam question. So each trial only has two outcomes. Do we recognize that? Hiya, welcome. Has two outcomes. So we typically think of it as like success or failure. Win, lose, this or this. Win, or I'll put success or failure. So that whatever the thing is, it successfully happens or it doesn't happen. That would really categorize it as whether it's binomial or not. So if you recognize that, that's brilliant. They're two of the conditions. Does anyone know any others? What else would tell us that it's a binomial distribution? So there's something else that has to be the same each time. It has to be fixed. So the probability of, like, say, winning or of success is fixed. Probability of success, which we're calling P, is fixed. It doesn't change around. And again, if we're thinking of this like a tree diagram, it's actually quite a straightforward tree diagram, but it goes on a lot. Like everything's got two branches and it could go on multiple times. And finally, the other condition we need to know, because they do test this, is all trials are what we call independent of each other. So whatever's happened before, it's not got like a memory. Each go, the probability is back to what it's doing every time. It sort of like resets, is independent of each other. And then finally, what we would say, and you might have seen this, is you should, so if we say in words, the random variable x, and we'll look at some of the very specific notation for this as well. The random variable, I'm going to use capital X, is described by a binomial, a binomial distribution. Then the way we will write all of this mathematically, which you may well have seen or not, we'll say with n trials, and P is the probability of success, we would write it like this. X follows the binomial with n and P. Now, you will do other distributions in year 13, like the normal distribution, but this is how we define it's a binomial, and that's the information we give. So the question could give you it like that, and that's just the kind of mathsy notation for it. Right, so I'm going to move on. We're going to look at some exam questions, and then we'll just build into the theory a little bit more kind of in depth. So just give me a 1, 2, or a 3 in the chat if you can, just to give me an idea of how solid your understanding is of this, how you're feeling with this stuff, just to sort of give me a sense. And then what we'll do is we'll do some couple of quick exam questions, see exactly how the stuff we've done comes up, and then push this a little bit further. So feel free to give me a 1, 2, or a 3. As I said, any questions you've got or answers as we go, do send them in as well, but this will just give me an idea. So otherwise we'll keep it moving. So if you think this is quite good, it's kind of revision, let me know. If it's kind of medium, let me know too. Hopefully you're not super confused, but if you've got any questions, do feel free to ask, but let me know in the chat either way. Okay, otherwise I think we'll push on to a couple of quick exam questions now. So here we go. So, past experience has shown that when seeds of a certain type are planted, on average, 90% will germinate. Sorry if that's a little bit cut off on the screen, but hopefully I'll be able to read it out and you can see that. So a gardener plants 10 of the seeds in a tray and waits to see how many will germinate. Name an appropriate distribution with which to model the seeds that germinate, giving the values of any parameters and state any assumptions needed for the model to be valid. So 4 marks is quite generous for this, but what we would say is we would say that X follows binomial distribution. N and P are the bits of information we need to give. So hopefully we can see, well, that's the number of plants and that's the probability of successfully germinating. So that would be 10. And I would typically give it as a decimal, but in the question, they might have given it as a fraction, decimal, or percentage, but that's how we're going to list it. So the answer is we're using a binomial distribution. And we'll think about why we've used the information that we did just to really clarify our answer to this question. So we know we've stated that the probability of success, like of successfully germinating, is 0.9. We know that the number of trials is 10. And then basically the things we are kind of the assumptions we've made. And this is where I think people get a bit nervous that they need to have like loads of like a massive knowledge base on what the topic in the question is, and you don't at all. You would have to just assume these things to be able to do this question in this way. So germination of a plant is independent of others. Because that is one of the conditions for it to be a binomial. And also the probability of that thing, whatever germination is, whatever that's doing, probability of germination is consistent, or is constant, sorry. So it doesn't change. So basically you're just doing the conditions you do know, but wording them back in context of the question. And 4 marks, that's pretty fair. I think that's quite generous. So the next one, let's have a little look. So on average, 25% of the packets of a certain kind of soup contain a voucher. Kim buys 1 packet of soup each week for 12 weeks. The number of vouchers she obtains is denoted by X. State 2 conditions needed for X to be modeled by the distribution that it's a binomial, where N is 12 and P is 0.25. So any conditions we can think of here. So key things we should be thinking. So they've told us something very specific, but we would have to assume, and do feel free to share any answers in the chat, or check if something you were thinking is valid, but probability of a packet containing a voucher constant. And they've actually specifically implied in this question that it's also 1 in 4, it's 0.25. And also, we would have to also consider that we think the event of a specific packet of a packet containing is independent of others. Okay, right. So we'll look at another quick question now and have a little think specifically about how you'd answer this one. Because again, this is just a nice, short, snappy exam question. And then we're going to move on to some harder examples. So last one of these for now. Andrew plays 10 tennis matches. In each match, he either wins or loses. Okay, so that's already lending itself to the binomial. Part A, state in this context 2 conditions needed for the binomial distribution to arise. Now, what we can't do is we can't say the probability is either success or failure, win or lose, is out of 2 outcomes, because they've actually told us that. So that's not an assumption, that's actually something that's given. This is really important. This is where a lot of students go wrong, because absolutely that's a sensible thing to say, but it's not a sensible thing to say you've assumed because they haven't told you it, because they have told you it. So we need to come up with 2 different things here. So 2 conditions, can anyone suggest 2 conditions that would also, if we're dealing with this tennis match scenario where you either win or lose, that we would also need to be considering as like a factor or a thing that we consider as given for us to use the binomial distribution? What would we have to make about the chance or the probability or of what's going on? Anything else that we would have to be assuming? So any suggestions, do let me know. And then what we'll do is, for these conditions, define the actual binomial distribution. So we'll do that for part B. So for part A, I would say the best things to suggest out of those conditions we listed earlier is that the probability of winning, and in reality, this might not be true. That's why it's an assumption. The probability of winning, because obviously winning a tennis match, there's a lot of factors at play. Probability of winning a match is constant. Okay, they haven't told us that, but we would have to work on that sort of premise if we're going to use the binomial distribution. Or we can't do anything, we can't use it otherwise. And we'd have to also assume each result is independent. So like if you've just had a win, that doesn't mean you're more likely to win another one or less likely because you're tired, which in reality it could be. But we're going to have to assume that each result is independent and every go it's that same probability of others. Does that make sense? Do let me know in the chat. And as always, guys, feel free to ask any questions as we go as well, or share any thoughts on these questions. And then we'll be saying it follows a binomial with n as 10 and p as, well, p, we don't know p, but we would maybe be given that. Is that all clear? So the thing we couldn't really say is we couldn't say there's only 2 outcomes, win or lose, and the amount of games is fixed at 10, because they're not assumptions, because they gave us that. So we have to kind of come up with the other 2 things out of the 4 we listed earlier. So if we go back and look at what we suggested, this was all the information we have to be able to sort of quote and relate to the scenario. So if they give us some of that already, we can't say we assumed it because they actually told us it. So that is really important, and they can be quite picky with this within stats. So that's how that relates to this question. Give the other information, not the bits they've told you. Cool, we're going to push on to some of the more tricky kind of content now. Binomial distribution examples. So I'm going to just move this on. And we'll look at the following. Now, some of you might know the calculator shortcuts. And if you do, if you know on perhaps the ClassWiz or whatever equivalent calculator you have for using for stats, you know a way to work out this probability using the PD function, feel free to do that. And feel free to share it in the chat as well. It'd be great to hear from you and get a sense of how confident you guys are with this topic. I'm going to go through it from scratch anyway to show everyone how to do this. But if you know how to work this out, feel free to do it at any point and share it in the chat, and we'll check that we all get the same. I will answer this question exactly how I would like you guys to answer it in an exam. So it says, at a bakery, there is 10% chance of a loaf from a batch being undercooked. Calculate the probability of there being exactly 4 undercooked loaves from a batch of 12. So I'm going to say let X be the number of undercooked loaves. And you should really state this. And I think this is a really good question to model this scenario. And I'm actually going to say X follows the binomial distribution with n as 12 and p as 0.1. Now, it's weird to think of it as like successfully being undercooked, but we want the chance, the probability to be that thing. We want it to be the probability of being undercooked. So being undercooked is like a little success. If it's not undercooked, then it's not what we're looking at. So this is important. So this is what we're saying. The probability here is the 0.1, it's the 10%. So if I want to work out the probability that X equals 4 of them have been successfully undercooked, then what we're going to do is we're going to do 12 choose 4 times the probability of being undercooked 4 times 0.1 to the power of 4 times the probability of not being undercooked, which is most of the time, to 12 minus 4. So essentially that ties up to 12 choose 4 times 0.1 to the 4 times 0.9 to the 8. And do let me know in the chat if you've got an answer to that. I'll give you a minute to work that out on your calculator if you've got your calculator there. And just let me know as well if you guys have seen the binomial PD function, whereby you can actually just type the NR and X in and it just works it out for you. And also, the other thing I'm going to say about the answer is I typically recommend giving the answer to 4 decimal places for probability, because a lot of the tables, the statistical tables in the back of the book and the formula booklet are to 4 decimal places. And I think it's just a sensible amount to go by, unless they tell you otherwise. So has anyone got an answer to this? Anyone got a solution here? Any ideas? Let me know. So hopefully if we've worked that out, oops, sorry. That's the value we find. Do let me know if you got that, and well done if you did. Any questions, let me know. But as I said, there is also a function on a lot of the calculators now where you can do binomial PD. You can put n in as 12, r as 4, and x as, p as 0.1, and it'll work it out. So that's really good if I think you might use nx and p. So that was good. So we'll do another one and see how we go. So calculate the probability of throwing exactly 9 sixes from 40 throws of a fair die. And I think they're talking about a fair 6-sided die. So let's set this up and you guys could perhaps go and find the probability for me. So let's say let X be the number of sixes thrown. And we'll look at the model it's following. And that will be X follows the binomial with the chance of it throwing a 6 as 1/6 and 40 throws. Okay. And we want the probability that X is exactly 9. So there's lots of different ways you could have 9 sixes, like 9 successful sixes. and as a result, 31 of the other thing, of anything else. So the amount of combinations will be 40 choose 9. That's like the amount of ways of arranging 9 things out of 40, and in turn restricting the other 31, times by a 6 to the power of 9, because that's how many we want of them, times by 1 minus a 6 to the power of 40 minus 9. So tidying this up nicely, let me know if you find an answer to that. Anyone got it? How do we feel with that? So I'll maybe give you a little bit more thinking time, because I don't want to keep rushing everyone. And as I said, you know, this is like a big kind of topic. This is something we do want to really understand thoroughly. But this is really going from scratch as well. So that process is hopefully nicely broken down. We can type that in. Remember that n choose r, 40 choose 9, 40 C9 on the calculator, times 1/6 to the 9, times 5/6 to the 31. These should add up to 40. That's how many of it happening, that's how many of it not happening. All the probability times together. And you might have also used the probability function. So does everyone know how to use that? If you've got the class whiz, does everyone know how to just type it in and it sort of all does that for you? Let me know. And thank you again for comments in the chat. Do feel free to ask at any point or share answers as well for this one. So do let me know if you've got an answer. It'd be great to get an indication of if we've worked this out, and also sort of sense checking it as well. So let me know if you've got a solution for this. That'd be great. And then what we'll do is we'll do a couple of sort of final exam questions to see how this will be really explored further in an exam. As many of you might know, it does come up in hypothesis testing, and it will be explored even further in towards sort of the end of the course as well. So we got an answer for this one. Let's have a little check. Okay. So I'll get the answer up shortly. Let's see what we think. Okay. So hopefully everyone can hear me. We're going to just check that. So the answer there, just under 1%, just under 10%, about 9% of the time. That would be the scenario we have. 0.0953. So giving it to 4 decimal places again. Well done if you got that. Just a 1, 2, or 3, guys. It'd be great if you could let me know in the chat, for those of you that are able to comment, just to give me an idea of how confident you're feeling with that, and how that's pitched. And if there's anything you want me to go back over, please do mention. Do feel free just to drop a 1, 2, or a 3 in the chat. 1 for if it's kind of straightforward, 2 for if it's okay, but maybe you think I'll need to work on that a little bit, and 3 if it's kind of confusing, because what we're going to do sort of to follow up is just do a couple of exam questions on that now. So just a 1, 2, or a 3 in the chat if you can, to let me know how you felt with this kind of question. And do feel free to ask about it, as I said, screenshot if there's bits that you want to sort of go over yourself in your own time. But if you can in the chat, that would be lovely to see. Otherwise, I'm going to move on to some exam questions now. Cool. Okay, right, thank you, excellent. So if there's any specific bits you would like me to go over, do let me know. But thank you for sharing how you're feeling, guys. And do be honest, like it's good to know. And it will be challenging because it's quite new as a topic. So if you're thinking it's okay, it's not something I'm super confident with because I haven't done a lot of it. It's new to me this year. I think that's absolutely understandable. If there is anything you'd like me to revisit though or re-explain, do let me know. But yeah, thanks for the comments, and anyone else wants to sort of suggest how they're finding it, please do let me know. Otherwise, I'll keep going on. As I said, happy to go back or answer any questions at the end. Feel free to ask them at any time. Right, this suddenly looks very full on, this kind of question, and it can be quite off-putting and daunting when you see a question like this. But let's break it down and it will be absolutely fine. So an express coach travels daily between Middlesbrough and London. When the coach calls at Thirsk, it's possible to purchase a seat on the coach, providing seats are available. The probability that the coach calls at Thirsk with at least one seat available on any particular day is 0.4. So that's the probability is 0.4 and is independent of that on any other day. Great. So it says calculate the probability that during a 28-day period, the coach calls at Thirsk with at least one seat available on exactly 7 days. So we want to now relate this to the binomial. Let me just check out it skipped one. Right. So let's think about how we'd answer this fully in order to gain all 3 marks. I think it's actually a really good question to look at in preparation for exams. So what I'm going to do is I'm going to say let x be the number of days. And this is a really important skill. I think I always kind of rushed this or missed this when I was doing my A-levels. I didn't realize how important it is to define the variable. So let x be the number of days that the coach calls at Thirsk, so calls, stops with an available seat. And because it's independent of the day, it is appropriate to use the binomial. So I would say x follows b is modelled by the binomial with n as 28, because we're looking at a 28-day window, and the probability that there's a seat is 0.4. Okay, and within that framework of that binomial distribution, we want the probability that over that time period, 7 days, there are some seats available. So we're looking for the chance that x is exactly 7. So that will be 28 choose 7. 28 minus 7, so 21. And let me know if you've got an answer for that. And again, 4 decimal places would be appropriate. And you might have used just the binomial function on the calculator. You might not have even had to do it necessarily explicitly like this, but hopefully this makes sense either way. Do let me know what you've got for that. If you've got an answer, I'm going to fill it in shortly. I'll just give you a quick bit of thinking time, and you can use your calculator to work that out as well. Okay, has anyone got an answer? Okay, I believe that's the value we get. Brilliant. Now, just as a follow-up for part C, it says indicate why a single binomial model would not be appropriate for the number of calls per month. Any suggestions? So this is a sort of quick one sentence throwaway comment answer kind of thing. Look at the information given. Why wouldn't it be appropriate to describe it per month? Now, this is really, hopefully, a fairly sort of basic question about times and timeframes and number of trials and stuff. But it is purely because the number of days in each month is different. It's not like fixed. So the number of days, this was given for 28 days, the number of days in each month, and therefore, and hence, number of trials, if we use this model, is not fixed. So it's not appropriate to use a binomial. So that's why it wouldn't be suitable. So that was quite a nice way of flipping the question round. Now, I think we've got one more past paper question to look at with this. Very well done, because we've kind of looked at a few ways this could come up today. So that was really good. The next one, it looks a little bit more kind of full-on pure mathsy question. A variable x has the distribution of being a binomial with n as 11 and p as whatever it is. And then they've said, given that p is 3/4 or 0.75, find the probability that x is 5. So this is a kind of straight on your calculator one, probability that x equals 5, using the binomial distribution. And I'm going to do it long ways, even though you know there might be some shortcuts on the calculator if you've got a calculator that has the binomial distribution. Otherwise, 1 minus 3/4 is 1/4, power of 6. 11 minus 5 is 6, and then we work that out, and I believe we're going to get 0.0268. Now, for part 2 here, given that the probability of x equals 0 is 0.05, find p. Right, this is interesting. So this is now saying, right, we've got x following the binomial with 11 and p is the thing we're looking for. So this is very different. This is a really good one to go through. And what we can think of is the probability of x is 0 is an interesting one, because n choose 0, you may know, is always 1. The probability of success is going to be p to the 0, so that's 1. So we're really looking up the chance of it not happening every single time, which would be 11 times. So we know now basically that 1 minus p, the chance of it not happening to the power of 11, would have to be 0.05. Now, before I move on, can I check that everyone understands that from that information? If the probability that there's no successes is 0.05, what it's basically saying is the probability of it being all failures times together, 1 minus p, like the opposite of it being a success, times itself, all 11 times, must be this number. And we're going to use that to work out what p would have to have been in the first place. Does the logic of setting that up make sense? Even if you think I would have struggled to see that, is that clear? That from this information, we can sort of reverse engineer it, and we can say, okay, the chance that there are no successes is 0, of no successes is actually 0.05. Then that means that times in all the other outcomes of being failures together to the power of 11 basically must equal 0.05, and that's now what we need to solve. Is that clear? And do feel free to say either way, because now we do still need to work that out. So what we could do is something to the power of 11. We can 11th root it on the calculator. And then we can rearrange this. Okay, and then obviously once you've got an answer, with a lot of the maths you do at A level, you can always put it back in and check it actually works. So that might be a good idea. So you could do 1 minus that value to the power of 11 and check it does come out as 0.05. So hopefully that's nice and clear. But yeah, 0.2384 for that one. And I think we've got one final question here, which is actually quite an involved one. But before I move on to that, I do just want to check we're all okay up to here. Please do ask me if there's any questions. If there's anything you'd like me to go back to or re-explain, that would be great. Let me know in the chat. But I think we've had a good sort of mix so far of different ways that this could come up in the exams. So do let me know if there's anything specifically you'd like me to re-explain or anything on this question that was a struggle. Otherwise, I'm going to move on. But yeah, I can still see the chat, guys, so do let me know. Right, here we go. Now this one is worth 5 marks. And it says the random variable x has a distribution with n as 21 and p as some value between 0 and 1. And it says, given that the probability that x is 10 is equal to the probability that the x is 9, find p. Now this is quite involved and hence the 5 marks. So I'm going to set this up. Because there will be a lot of method marks up for grabs, even though this is a difficult question. So what we should probably do is start by really carefully, not just turning to the calculator straight away, but looking at the kind of formulaic way of doing each thing. So 21 choose 10 times p, whatever p is, to the power of 10, times 1 minus p to the power of 11 is out of 21. And that would need to be equal to 21 choose 9. Oops, hang on. Because this would certainly be your first mark or couple of marks. Everyone happy with that so far? Because this is a key thing for A-level maths, is that we can start it off, we can get the method marks, because unlike GCSE, you don't get a lot of marks for the answer. It's all method, lots of show that, lots of proof, lots of show you're working. Is that clear up to there? So that's sort of the first thing we can really do. That's one of the few things we can do, is just find the sort of formula in terms of P of each thing and equate them to each other. And then it's a case of seeing that through. Now, this and this at the moment are the only things we can actually work out on the calculator. So I'm going to keep going because it's going to look quite involved in a second. That's quite a big number. And this number here. Okay, and now it's just about rearranging it all. So I'd actually bring it all to the left and then try and factorize. So get it all on one side equal to 0. And this is a really good skill for going forwards, because it looks like a very nasty thing to factorize, but it actually factorizes quite easily. So I've literally just brought that to the other side. And then we've got a common factor of p to the 9 is the highest common factor. That could come out. And also 1 minus p to the 11 can come out. And what's left in here is actually, let me just have a little look. Yeah. 3, 5. Times another 1 minus p. So I've factored out a p to the 9, which still left a p for this bit, and 1 minus p to the 11, because now I can start solving it. And this is a kind of factorizing skill I've seen a lot in pure maths as well, when people have struggled with. But well done if you followed it up there. Do feel free to ask if that's unclear. Now, if we expand this a bit more, minus what we got there, 293,930 times 1, and then times it by minus p, that bit can be tidied up with that bit. So you'd end up with plus 293,930p. So you actually end up with the following: p to the 9 times 1 minus p to the 11. And then we actually end up with 646,646p minus equals 0. Now, if we solve this equal to 0, the factor we can use to solve is actually this one. When would this bracket be 0? When would 6,466 equals 0? Well, if you rearrange, plus that across and divide by that, you get p is equal to which I believe simplifies to 5/11ths. Let me just check. But do let me know if there's any questions on that one. Yeah, so quite nice. Very involved, difficult question for 5 marks. But then at the start, there was really only one way you could go. And then it's about sort of persevering and seeing that through. So let me know if there's anything you'd like to check on there. And then we'll just round a few of these bits off. Okay, so that was quite a lot of content, quite involved there with what we did today. But we've looked at the binomial expansions. We've looked at actually the criteria for the binomial distribution and under what conditions we would use it, and then actually calculating probabilities from the binomial. So that's been quite a big thing we've done today. If you have any questions for me, do let me know. What I'm going to just do quickly there, thank you very much for everyone taking part in that. I do just want to quickly take you over to Snap Revise. So if you haven't looked on here before, there's so much content on there for you to kind of go through and have a little look at. Revision sessions, exam technique, there's absolutely loads. So the web classes, so do sort of explore that. If you haven't sort of looked on there before, we've got exam packs. It's all tailored to the new exams, so really worth looking at. And obviously we have the YouTube live sessions on Sundays, but there's so much more on the platform in terms of resources that are tailored to all the exam boards and to all the new exam content as well. So it is really worth checking out. Thank you so much for working along with that content today. If you've got any questions, do let us know. Otherwise, hopefully we'll see you at another session soon. But really well done, and have a good rest of the term. If you're still at school, still working, good luck with it all, and a good Christmas period and a good break and a happy new year as well from me. But well done today. Thank you so much for working through that alongside me there. And yeah, hopefully see you at a session soon. Thanks very much, guys. I hope that was useful, and take care, keep well, And thanks again. Cool. Well done, guys. Bye.